Hello, everybody, and welcome to night two of CRAM season with Fiveable for AP Stats. So we are going to be here for 5 nights, and this is night two. So we are super excited to be here with you all tonight. So before we get started, and we talked about this the other day, some community agreements that we just want everybody to make sure we have in mind as we are going through this learning process together. Number one, make sure you are supportive of each other. The chat was hopping last night, and we had a lot of fun hopping in there and helping each other out and taking part in that learning procedure together. So we definitely want to make sure we are continuing to do that. Also, be patient. We got 5 nights, so 3 hours apiece together. So be patient with each other. If you see the same questions being asked over and over again, just be patient, knowing that we are we're all in this together, this AP cram season. Also be kind to each other, and also be kind to us and our student hosts and everything. um, you know we are human. Things happen. Last night there was a little typo on the slides. We corrected it real quick and everything was good to go. So we just wanted to make sure that y'all agree to be kind to us as we are all going through this, and kind to each other, obviously. So the ways that you can make the most out of a cram finale. Number one is take notes. So you can see the call to action down below where you can find your slides and your cheat sheets that you would need. Do something to be active, taking notes, being active in the chat, asking questions using that Q&A tab as well. You can see both of those things over there on the screen as well. Also take advantage of the CRAM Hub. It has the slides, it has the study guides, all the replays for you, all the things that you might need. That is in that CRAM Hub for you that can help. Also, we will take breaks, and the replay for tonight will be available immediately after the event. So yeah, we're in night two. It is May 3rd. It is getting closer and closer to May 7th. My name is Josh Argo. I'm the teacher host. And I'm most of the time just going to be in the background helping out with a few questions towards the end, maybe. And then we have a team of 5 student hosts who are doing a fantastic job, who have worked really, really hard to bring you the best version of AP Stats that they can in these 5 nights. We also had 2 awesome designers that helped put the slide decks together. So we want to recognize them. And I am going to let one of our student hosts, who is going to be presenting tonight, introduce herself.
Hey everyone, I'm back. I'm Emily. We have Miriam as well, but she is stuck in some traffic. But yeah, I will be teaching you guys a little bit of probability today. So I know you guys hate this, but I hope we can make it fun.
Yes, probability is everyone's stressor. I feel like whenever I ask my students, hey, what is it that you need help with, it is always probability, which brings us to our agenda for tonight. So the first thing we're going to do is we're going to hit all those nasty definitions from experimental design. That's unit 3 on collecting data. And we will, of course, have an awesome cram quiz. The fantastic music that has been stuck in my head all day today is going to be back for the cram quizzes, and also we will have a PEP statistical escapade, which is the free response initiative that we've taken for our AP Stats cram season. There's a chance for you to work it out with us and then check your answers, which is great. That is the best way to do free responses. And we'll talk more about that as we get there. We'll have a little break for Q&A, and then we'll hop into Unit 4, which is the probability unit that I'm sure a lot of people, based off of the feedback we've gotten, is what people are really looking forward to getting some help with. And we will do everything we can to help you prepare for the probability-free response, along with the probability multiple choice that will come your way. All right, make sure you follow Fiveable on social media, LinkedIn, YouTube, TikTok, Instagram, all those wonderful places. There's tons of awesome content from student creators and teacher creators that can help you to maybe laugh a little bit, maybe prepare for AP or ACT tests, any of those things like that. All right, so tonight, like I said, we're going to be talking about Units 3 and Units 4. Unit 3 is on collecting data, which is experimental design. That makes up 12 to 15% of the exam, which is a pretty large portion, and a lot of it is vocab words, and we are going to break down all those and kind of hit the points that are more confusing for us as we've kind of learned it and as I've taught it. So we will definitely be going over those definitions and how those things are different. And then Unit 4, probability, which maybe this can ease your anxiety a little bit, actually only makes up 10 to 20% of the exam. It's a whole lot of stuff, but kind of a smaller portion of the exam. But we will cover everything that you should need to know to be successful on the AP exam for that. Again, like we mentioned last night, the way the test is broken down, you have 90 minutes for 40 multiple choice questions, which is half of your score, and then 90 minutes for 6 free responses, in which one of them is a little bit longer as well to take on, which is your investigative task. All right, and I'm going to pass things off to our student hosts as we dive into collecting data.
Alrighty. All right. So collecting data is our Unit 3. It accounts for about 12 to 15% of our exam. Next. Okay. How do we want to plan a study? Okay, so our first option is going to be defining our objectives. We need to identify our sampling method, whether it be stratified random sampling, simple random sampling, cluster sampling, anything about that. All right, and then we're going to want to define our population. Maybe we could say like juniors or seniors. And lastly, we want to make sure we consider bias and error. If either of them is wrong, the results will not be correct. All right. Now we want to choose our population. Remember, a population is an entire group of individuals, which you most likely will not be able to collect data from. So usually we use a sample, which is a subset selected from a larger population. So maybe instead we would sample juniors or seniors at a local high school. Lastly, we have ethical considerations. Make sure these are included, whether it be like keeping everybody anonymous, whoopsies, confidential information, or make sure they feel comfortable answering your questions. Like, don't like come up to them and be like, you have to answer this or I'm going to fight you, because that's not going to work. Next. Okay. Observational studies are when researchers observe and collect data. Remember, there is no treatment imposed. You don't force them to like eat some medicine or anything. It's just, after all, it's a study, not an experiment. Sample studies are a type of observational study where data is collected about a sample from a specific population. So maybe it could be favorite ice cream flavors of high schoolers, and maybe I could go to like a local high school and be like, ask people like, oh, what's your favorite ice cream? That's kind of creepy, but if you want to do an experiment, do an experiment, a study. Next. All right. Random sampling. Why do we want to do random sampling? This helps get rid of bias. So like, let's say this huge horde of people is coming in. If you ask every single one of them, they're likely going to have the same answer. Or even if they don't have the same answer, they're still going to be like, oh, if my friend said this, I kind of want to say that too. It's going to basically result in a lot of bias, and it's going to lead to like inclination of answering the way you want them to. So if I asked like 10, like a horde of people, I wouldn't feel very comfortable like generalizing that to a whole audience. Maybe if I chose like simple random, like if I did sample random sampling instead, I would feel a lot more comfortable generalizing that to like the United States, if that makes sense. Oh, it's Pep. All right, there are 5 types of random sampling. Our very basic first one is simple random sampling. So let's say you get a roster of people in the class, like, I don't know, like your AP US history class, and you put them all in that little like spinny wheel, like the spinny wheel generator that teachers use to call on people with. If you spin that, everybody has the exact same probability of being chosen. So it's very simple. Remember, it's simple random sampling. It's very simple, and there's no caveats at all. Next, we have stratified random sampling, where we split them from like a specific category. So maybe we're splitting them like by gender, and then we randomly sample each of the groups. Next, oh my God, there's a fruit fly in my room. Next, we have a cluster, where we divide a population into a certain amount of clusters, and then we randomly choose a cluster. So maybe we have like 20 people, we split them into groups of 4, and then we randomly choose a group of 4. Oop, back one. Okay, perfect. All right, so Pep is terrified. He says more. He's terrified amount of random sampling there is, but that's okay. There's only two more. Systematic is our type where the AP Stats kids at my school use. They come up and say like random stuff. It's kind of scary. They're like, "Oh, do you support the inhumane killing of animals for food?" And I'm like, "It's 8 a.m. in the morning. I don't want to answer that." But they basically count and they see like, "Oh, every fourth person or every 10th person you ask." So remember, it's systematic. So like every four, every eight, it's like in a block. So remember, it's not like simple random where you just take random people. It's every certain amount of people. Census is one of the biggest or most accurate ways to collect data. The government is one that uses the census. We do a census every 10 years, and that's everybody. So that's why they do it every 10 years, not like every day.
Okay, so now we're going to be talking about some types of sampling bias, which can affect the accuracy of our data and like what we can generalize it to. So the first is voluntary response, which happens when you have a sample in which people choose to participate in a study. So if I'm like giving out this form to everybody in this meeting, and only some people who want to do it decide to fill it out, then that's an example of voluntary response bias because it's not representative of everyone. So if it's about a particular topic that some people care more about, they might decide to fill out the form while other people don't fill out the form. So that's a type of bias. So we want to avoid that. Okay, our next type is undercoverage. So undercoverage bias happens when a portion of the population has a reduced chance of being included. So that's also not representative. So for example, if you sent a poll out on Instagram and not everyone has an Instagram account, then that might be an example of undercoverage bias because those people are not being represented in our study. And that's especially important when our study might have something to do with that type of information. Like, for example, if it's about what type of social media people use the most often and we post it on Instagram, then that would be an undercoverage bias because our topic is related to social media, but some people are being underrepresented in that sense. The next type is non-response bias, in which individuals are chosen for a sample, but we can't get data from them. And this is important because the people who respond may differ from the ones who don't. Like, for example, if we choose random people to give our survey to, but they don't respond, for example, maybe they're like too young to understand, or like they're too old and they don't like using technology or something, then those people are going to be different from the ones who did respond to our survey. So that would be an example of non-response bias because they're not responding for a particular reason, and that makes them different from the rest of the population, but they're being underrepresented in our sample. The next one is question wording, in which question in a survey influences the response. So it can be confusing, misleading, or ambiguous. So I think Emily was talking about before, like if you're talking about the inhumane killing of animals, then that's different than if you're just talking about animal testing, because animal testing is more neutral, whereas if you're talking about the inhumane killing of animals, then that could be more biased and that could influence the way people respond to your survey. And another thing that is also related but not exactly the same is who is asking the question. So for example, if a police officer asks if you ever got away with a crime, then you're going to respond differently than if somebody else like anonymously asks you the same question. And the last type is convenience sampling, in which are selected based on availability, and these are just not represented. So like, for example, if I just stood at the gate of my school and just asked random people, like the first like 30 random people that I found, which to fill out my survey, then that's convenience sampling because they're convenient for me to find, but it's not represented of the entire population. Like, for example, if the entire population is everyone in my school, that's not really represented by the population that I chose that was convenient for me. Okay. Next slide. Okay, now we're going to be moving on to experimental design. So an experiment, as opposed to a study, which Emily was talking about before, is a research that studies the relationship between variables. So in an experiment, researchers impose treatment on a group and compare it to a control group. So you have two groups, one receives the treatment and one either doesn't, or they receive a different type of treatment, and then you're comparing them. And this is not like an observational study because for an experiment, we're imposing treatment, and that helps us to determine a cause and effect relationship or some type of relationship between the variables. And you can also generalize experiments where you can't with studies. Okay, so here are some components that we need to know for an experiment. So experimental units are the individuals or objects that are assigned to treatments. Treatments are the conditions that are applied on an experimental unit, and a control group is a group who's not exposed to any treatments or placebo. So for example, if we wanted to test the effectiveness of a certain type of medicine, sorry about that. That was my sister's alarm. Okay, so if we wanted to test the effectiveness of a certain type of medicine, and we had different groups of people that we randomly chose previously, and one is the control group and the other one is the non-control group, and we would give one of them the medicine and we would give the other one no medicine. And so here in this example, our control group is the people who don't get any medicine, and the other group is the one who does. Our treatment is the medicine that they're receiving, and the experimental units are the people who are participating in the study because they're the ones who are being assigned the treatment. Next slide. Okay. So here are some more components that we need to know. Response variables are the outcomes measured. So in our example where we're talking about people who are receiving a treatment, if we're trying to measure their recovery to a disease perhaps, then the response variable would be like the thing that we're measuring. For example, if we're measuring like their blood glucose or something like that, that would be our response variable because that's what we're measuring to see whether or not the treatment affected them. The explanatory variables are the variables manipulated. So if we're giving the medicine, that would be like kind of like our explanatory variable. And confounding variables are outside factors that affect the relationship between variables. So these are usually things that we want to avoid. So for example, if whether a person knew that they were receiving a treatment, that could be a confounding variable because they're just thinking that they're getting better even though they're not. Or if based on the place that they're at during the time that they're taking the treatment, that might affect it, or their outside activity, like whether they exercise a lot or things like that, that might affect how they recover to the thing that you're trying to measure. So these are things that we usually try to control for because they can affect our experiment, like they can make it seem like there's a relationship between the two variables when there actually isn't. Okay. Next slide. Okay. So here are some principles of design that we need to know when we're either designing an experiment or looking at whether an experiment is an effective way to measure something. So the first one is comparison. So you need to make sure you're comparing at least 2 treatment groups for it to be an experiment. And one of them should be a control group that is not being affected by the treatment, or could be a control group that is not being affected by the treatment. Or you could have like 2 different types of treatment or multiple different types of treatment, and you're trying to compare them with each other. So comparison is an essential part of the experiment process. Okay, the next one is replication, which is important because it ensures validity, and it's not like just one anomaly or one random thing happened and that's why we get this relationship. So we're making sure that if we keep replicating our experiment, then it would be producing similar results. So the same responses mean that your conclusions and analysis are correct. So they're like validating your experiment. And this can be in the form of like having multiple people in a group instead of just one person, or even doing the experiment multiple times, that sort of thing. The next thing we need to focus on is randomization, which means that random assignment of treatment to units. So even if we choose the people that we're doing randomly, we also need to make sure that when we assign them to the different groups, that's also random. So that's random assignment. And this helps because it controls confounding variables and it eliminates large differences. So if we're just choosing like, if we have a random group of people and then we put all females into one group and all males into another group, that could be a confounding variable because that could affect our experiment even in ways that we don't know. So to avoid that, we're just going to randomly assign them to eliminate the possibility of getting anomalies based on that. Okay, the last thing we need is a control group, which is a group that is not given a treatment or that's given a placebo. So this makes sure that outside factors are not affecting our relationship, and that we need something to compare it to, right? Because we need to know whether this is just the normal thing or whether it's being influenced by the treatment. And a placebo is where like you give a fake treatment basically. So it's kind of like if you have in the previous example where we were talking about you're giving people pills. So you have another group that you give a fake pill basically, so they think they're receiving the treatment even though they're not, because the placebo effect is where if people think they're receiving the pill, they might think they're getting better even though they're actually not. So to eliminate that, or to eliminate that confounding variable, we would have a placebo or a control group. Okay. Next slide, please. Okay, now we're going to talk about blinding methods. So single-blinded is where subjects don't know which treatments they get, but the researchers do know. And double-blind is where neither the subjects nor the researcher knows which treatment a subject is receiving. So this can help if we're in the earlier example where we're talking about a placebo, where somebody's receiving a fake pill, so they don't know if they're actually getting better because, where they don't know that whether they're not receiving the treatment or not. So their getting better would be as a result of the actual treatment and not just their own intuition. So this double blinding and single blinding helps because the experimental units would not be affected by whether or not they know which treatment they're receiving. Okay. So there's several different types of experimental designs that we need to use. So it's important to know which one we should choose. So the first one is completely randomized, in which subjects are assigned to treatments by chance. So this is like using the other randomization processes we talked about before. So it can include using a random number generator or a little spinny wheel like Emily was talking about. The next one is randomized block design. So blocking involves dividing groups into blocks by blocking variables with similar physical characteristics. And that can also help reducing for confounding variables. So for example, if you wanted to test the effect of a certain product and you wanted to test the effect of the same product from two different stores or two different companies, then you could block them to put the two different ones as separate groups. So that would not be randomly assigned since you already know that they're two different groups. But that could help to reduce the confounding variables. And the last one is a matched pair design, where you use a blocking variable to form pairs, and each pair receives both treatments.
All right, so I'm going to ask you guys some questions of kind of like checking if you guys understood what we just taught you guys. You guys can just answer in the chat. All right, our first question is, how does random sampling contribute to the reliability of statistical conclusions? If you guys have a good answer, I'll pin it, so. All right, we have a good amount of answers in the chat, but the main thing we were talking about is it helps avoid bias. Yeah, the answers are coming in. All right, good job, guys. Next question. Describe how to create a simple random sample. Remember, simple random, it's simple. There's no like caveats or anything. Okay, so I pinned one that says draw names out of a hat. That one is something my teacher taught me. That one's a really good one. You can also label or you can random number generate. There's a lot of ways you can do it. Just make sure it's totally like simple random stuff. Like there's no weights or anything on certain numbers. All right, describe how to implement a completely randomized experiment. All right, we have some good answers in the chat coming in. We have a couple of different good answers. Waiting for maybe a couple more answers. We have like four-ish right now. Get like two more good answers. All right, someone on the CRAM host team seems to like Sonia's answer. So after randomly assigning all your subjects treatments, give your control group a placebo, treatment group the treatment, then analyze their results. And as Cindy said, make sure the treatment is always randomly assigned. Good job. Next, describe difference in observational studies and experiments. No causation versus causation, not randomly assigned treatments, etc. Yay, okay, we got a good answer from John. Jennifer, Tara. Yeah, we have a bunch of good answers coming in. All right, so observational cannot prove causation, only correlation, while experiment can. Good job. Sorry, that is the neighbor's dog. All right, explain how blinding can reduce bias in experimental studies. All right, I am trying to get as many answers pinned as I can, but all of you guys are very good. So there's no researcher bias, there's no placebo effect. Basically, no bias gets put into the study from a lot of different factors. All right, it's time for PEP statistical escapades. Should I read this whole thing? I'm gonna refrain. I'll read the second paragraph. All right, a new medicine has been implemented in a study with 100 pepper volunteers. The researchers randomly assigned the 100 peppers to 4 treatments: 0 milliliters of new medicine, 5 milliliters of new medicine, 10 milliliters of new medicine, and the previous existing yet not very effective medicine. After a few weeks of taking the new medicine, the rotten symptoms are observed again and seeing if they improve. Guys, please save Pep. Get your answers right so Pep is alive. He looks like he's struggling. Can we get the part 8 up, please? All right. Identify the following aspects of the study Pep has found. I believe there's another part. Yep. Experimental units. I need to see spam in the chat with all the right answers, please. The chat is blowing up too much for me to accurately pin an answer, but everybody is going. I love the emojis, Maddie. All right. The 100 peppers. Good job, guys. Next, part B. Identify the following aspects of the study Pep has found. Again, explanatory variable version. All right. There are a lot of good answers in the chat. We are looking for the dosage of medicine. All right, last part. Maybe it's not the last part. I think there's one more after this. What is the response variable? Alrighty. So, as it says in the question, the rotten symptoms are observed again and seeing if they improve. So, we're looking at the rotten symptoms and if they improve or not. Good job. Maxwell just came up with that answer. All right, part 4. What are the treatments? This is where I believe Cindy was asking a question about. Maybe this will come in handy. All right, we have some good answers. We have some people that got trapped. That's okay. Remember, you got to include the old medicine in this. So you have 0 milliliters, 5 milliliters, 10 milliliters, and the old medicine. Next, okay. Describe how researchers would randomly assign treatments to the treatments above. This is, I believe someone was asking about this. Don't we have to mention random assignment? Yes, you can now give a whole yapping about it. All right, I believe Jennifer has the exact answer the answer key had. You guys, all of you guys have really good answers. I will just go up and pin aggressively. If you don't see your answer pinned, just imagine that it was. Maybe it was for a millisecond. Alrighty. So I will read. Oh, goodness, that is small. All right, I will read the answer key. In order to randomly assign treatments to rotten peppers, researchers would assign each pepper a number between 1 and 100. The researcher would then use a random number generator to generate 25 unique random numbers between 1 and 100. These peppers would be assigned to 0, and then you just continue with the remaining numbers until you get the remaining 25, and then you get that as the ones going to the old medicine. Is this an experiment or an observational study? Justify your answer. Please don't go 50-50. I need the justification. Alrighty, we have a lot of good answers. Experiment, 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 experiment. And we have some good explanations as well. Let's see if I can find a good one. Mr. Argo, with his Mr. Teacher mode, be sure to include context in your answers, be as specific as possible. I like Ari's answer. Tara's answer is good as well. There's a lot of good answers up here. So remember, it's an experiment. There are treatments. And since the dosage treatments were randomly assigned, this is an experiment, according to Fiveable. Next. Perfect. All right. Upon finding significant results, the researchers claim that the new medicine causes a decrease in the nasty symptoms. Pep is looking very excited, guys. Is this a claim of causation? Is this claim of causation correct? Justify your reasoning. All right, we have like 15-ish answers. Miriam. Alrighty. Um, this claim of causation is correct. Why? Because it's an experiment, and causation can be established with experiments. And there was no bias. Good point, Jennifer. All right, guys, it's samosa time. Get that link. If anybody does not have it, oh, it's a call to action now in the it's that green link down there.
Okay. The first question is, if researchers select every nth individual from a list for their sample, which type of sample are they using? I think this one should be pretty easy, guys. You guys, let's see if we can get it to 100% participants. One more. No? Okay. Okay. Oh my gosh, 95% got it right. Okay, so the answer is systematic sampling, which is where we select every individual from the list for the sample. And like when we have systematic random sampling, we would like randomize the first person, but then after that, we would select every nth person. Looks like you guys got that. Good job. Woohoo, we got 100% participation. Okay. So this question was, how does voluntary response sampling introduce bias into the survey results? Okay, looks like most of you guys got it right. So the answer is, it means only those with strong opinions or interest in the topic are likely to respond, creating unrepresentative samples. So voluntary response is where people who self-volunteer for the sample are the participants, and everyone else who is not that interested in it, just doesn't choose to fill it out. So that means that those with strong opinions or more interest are more likely to respond. And that's unrepresentative because The other people who are less interested are less likely to respond, even though their opinions might be valuable to include. Okay, yay, we'll see you guys got this one as well. So, simple random sampling is the one that ensures that every individual in the population has an equal chance of being selected. Because, okay, so this was one. Okay, so in a study on eating habits, if researchers use voluntary sampling from an online health forum, which of the following is the most likely bias introduced? So the answer is self-selection bias because the people are self-selecting them for the study. So self-selection bias is kind of similar to voluntary response bias because they're self-selecting them or volunteering for the study. Yeah, it's basically the same thing. Okay. Okay. This one says if the researcher uses data from an online forum to conclude about the popularity of various music genres among teens, what type of bias is most likely to be present? So this one's also voluntary response bias since the people are like volunteering for the answer. But I can see how it would also be undercoverage bias since people who are not online would be underrepresented. So yeah, I guess they could technically both be considered correct. Would it be represented? Oh, sorry. Okay. Most of you guys got this right. So if a pollster only surveys individuals in urban areas, that would mean that people in other areas like rural or suburban areas wouldn't be as represented. So that's why it's under coverage. Okay, so which of the following is a key characteristic that distinguishes a well-designed experiment from an observational study? So, one of the characteristics of a well-designed experiment is random assignment. Remember, the other ones were comparison. It's gonna come to me. Don't worry. Okay. And then one of the common distractors was a collection of data without manipulation of factors. Um, I guess that could make sense, but a more explicit way to say it would be random assignment to treatment written groups and talk about treatment. Okay. Okay. When individuals want to control for specific variables by grouping similar individuals together before randomly assigning them to treatments, that is block design. It's not matched pairs design, because matched pairs is when there is only two groups, whereas block design can be any number of different groups. But the important thing to consider is when you're grouping them, that you're grouping individuals that are similar in order to get rid of confounding variables that might otherwise affect the results. So matched pairs is a type of block design that only involves two groups that are the same size. Oh, looks like this was a tough one. Okay, so it's asking about the mean effects when you have two different teaching methods on standardized test scores across several schools. So, in order to reduce the variability due to differences among schools, the schools here is being considered as it could be a confounding variable. So, in order to reduce the variability due to the differences between schools, we would block them. So, we would put different schools, and then within each of those schools, we would randomly assign them to teaching methods and treatments within each block. But since the school itself is a confounding variable, we would block them by each school. It looks like some people thought it was A, which is a completely randomized design with students randomly assigned to either teaching period without considering their school. So since the question is asking us to reduce variability due to differences across the schools, we would consider that confounding variable, and we would need to block that, because if we just piled them together and randomly assigned them, we wouldn't be able to detect the variability due to differences among schools. And then some people also, oh, sorry. Okay, so this question is asking what type of experimental design should be used when we're studying the impact of exercise intensity on heart health, whereas subjects vary widely in age and fitness level. So this one we would use a stratified random. I don't know why it's so bright all of a sudden. We would use a stratified random sample, dividing subjects into strata based on age and fitness before randomly assigning treatments and exercises internally within each stratum. So stratified random sampling is when we divide them into groups and then we randomly pick individuals from each group. So it's like a different type of random sampling. And it looks like some people thought it was D, which is a simple random sample assigning individuals to different levels of exercise intensity regardless of age or fitness level. So that's kind of like in the last question, it's never a good idea when we're trying to get rid of confounding variables to just ignore them. We should instead decide to, if we're assigning them, to block them, or if we're trying to sample individuals, we would do a stratified random sample. Okay. Okay. This question was asking in an observational study where researchers found a strong association between exercise frequency and reduced stress levels, which statement describes an inherent issue with this conclusion. So the answer says that the association does not necessarily imply causation because there could be lurking variables present. So that's just talking about how, because it's an observational study, we can't infer causation from it because there could be like confounding variables that we're not even considering since we're not even assigning the treatment. Yeah, looks like a lot of you got this one. So now it is the time for break. I know you guys are happy about that.
Alrighty, we are back from break. I'll give you guys like 15-ish seconds to get back. I need to turn on my camera and get back as well. All right. It is probability time indeed. I know you guys are very excited. All right. All right, probability. So probability models describe chance processes and are used to represent likelihoods of different outcomes. Randomness. All right, so I'm sure you guys know what randomness is. This is a good definition for statistics. When the data contains no recognizable patterns, and so outcomes cannot be predicted with certainty. So kind of like the residual, our residual is randomly scattered. So that's an example of something that is random in statistics. Our outcome is a possible result of the chance processes. Our sample space represents all possible outcomes of the chance process. So let's say we're looking at a dice. The outputs we can get are 1, 2, 3, 4, 5, and 6. So as I can see the dice roll. And then event is a combination of outcomes. So an example is like, oh, we can get a sum of 6 for 2 rolls, which could be like 2 of 4, 1, 5. You could do 3, 3 as well. Next. All right. So we have some basic foundations or rules of probability. So first, we want to have the probability between 0 and 1. Like we can't have a probability of 2 because 1 is basically it happens every single time. 0, it means it can't happen at all. Like flipping, wait, that's not good. Flipping like, I don't know, some random side on something that's not heads or tails on a coin. You can't do that. 1 is like a coin that's tails and tails on both sides, and you flip a tail, that probability would be 1. So our total probability always needs to sum up to 1. So let's say when we're flipping a coin, what's the probability of a head or a tail? It has to be 1 every time because it's either a tail or a head. And then our complements are the probability that the opposite of an event occurs. So let's say we're trying to calculate if we flip a coin like 3 times, the probability that it gets heads at least once, then we would do 1 minus the probability it gets just 0 heads, so no heads at all. Complements are very useful when you're calculating some very long, that's okay. Complements are very useful when you're calculating like, oh, the probability you get like 6 heads, at least 6 heads in a roll of like 10. You can simplify your calculations a lot by just doing the complement instead. Next. Alrighty, what is a simulation? So we had a little talk about the random number chart in the chat before. That's a little picture of it. You can use this for a lot of different like implementations of the experiments you guys want to make. So what is a simulation? A tool that generates synthetic data based on a model or certain assumptions. It's used to explore behavior over different scenarios, provides insight into real-world patterns. So how do you conduct a simulation? Describe how each trial of a simulation will be represented, what chance device. So you could use the random number chart for this one, or you could do a slips from a hat like the index cards. You guys could use a random number generator, whatever you guys want to do. Just make sure there's no bias at all. And then we'll perform Venn trials. You got to make sure there's no there might be a mistake in the first one. You want to do repetition to make sure. And lastly, we use the results to answer the question of interest. All right, so we have some rules. First, we have the law of large numbers. Simulated probabilities tend to get closer to true probability as the number of trials increase. So let's say we have a coin and we flip it once and we get a head. So the probability of a head is going to be 1. But normally, the probability of a head is definitely not 1. It's actually 0.5. So maybe the next time we flip it, we get tails. And that way it's 0.5, 0.5. We want to flip a big amount of times so we can actually get an accurate true probability. Flipping it once is very inaccurate because it's going to be 1 and 0. It's going to be split as one of them is definitely 1 and the rest are 0. Make sure you guys, as you guys do it more, you'll get more flips of like the tail instead, and you'll even out the probability of each one happening, which is more accurate. Our addition rule, PA, probability of A union B, which is A or B, is probability of A plus probability of B minus probability of A, that's probably A or B equals probability A plus probability of B minus P of probability A and B. So let's say one is Pep is happy and Pep is smart. So probability of Pep being happy plus probability of Pep being smart minus probability of Pep being happy and smart. So we want to take out the cases if it's not independent of the ones where there's an intersection, because then we're overcounting probability and the probability might even go over 1, which is just not accurate at all. Make sure that you have the and there, subtracting the ones where they intersect. So this applies to or probabilities. Our multiplication rule, if two events are independent, probability of A, that's the A and B equals probability of A times probability of B. And this is and probability. So like Pep is happy and Pep is smart is both of those.
Okay, so these are some different representations that you can use to show probability. So one of them is a tree diagram in which you can visualize multiple stages, and it demonstrates conditional probability based on the outcome of previous stages. So in each branch, you would write the probability of each of the different events occurring, and if there's different successive events, at the end you would multiply all the different probabilities in the branches to get the probability of all those events occurring in succession as an A probability histogram has the possible outcomes represented on the x-axis, and the y-axis represents the probability of each range of outcomes. A Venn diagram helps to visualize unions, which are both of the circles, and the intersection, which is just the overlap. So that can help you to visualize the or and the and. So unions is everything that happens within the two circles, and the intersection is just the middle, which is the and, whereas the union is the or. Next slide. Okay, and another way we can use to represent it is a two-way table. And we've seen these before. You just have different categories on the X and Y, or like the left and the top. And they show the frequency of each combination of categories between the two variables. These are useful for calculating the conditional probabilities, which is the probability of one event given that another event has already occurred or is certain. So in order to do that, you would find a cell where the two of them overlap, and the denominator would be one of the totals of that column that is the given part. And a joint probability is the probability of a single event, which represents two events occurring together, the probability of a single cell, which represents two events occurring together or an intersection. And in the two-way table, that's represented by one cell in which a column and a row intersect. So that's also an example of and. Okay, next slide. Okay, here's a check for understanding. So using the two-way table to the right, or to the left, what would be the probabilities for a conditional probability, which is male given sports car? You guys can type the answers to that in the chat, what you think the probability of male given sports car would be based on the table. Okay, I think I see a lot of right answers in the chat. So for A, or so for the first part, male given sports car, the probability would be 39 over 84. Since the sports car is given, that's at the bottom, since that's all the people who have sports cars. And then based on that, the probability that you are a male, that would be 39 because there are 39 males who have a sports car. Okay. And another formula that represents the same thing is that in a given situation, if you had at the top, you would be male and sports car over the probability of just sports car. Okay. And then for the second part, what is the joint and intersection? So what is the probability of female and SUV? Okay. So for this one, the probability of female and SUV is if you look at the intersection where the cell where a female and SUV intersect, there are 135 people who are female and have an SUV. And then out of the total of the entire table is 240. So the probability of female and SUV would be 135 out of 240. Okay, so for the last one, which is a union, what is the probability of female or sports car? Okay, so the probability of female or a sports car, I know I saw some people saying that in the chat as well. So the probability of being female is 180, and the probability of of owning a sports car is 84, but there's also some overlap, so we need to make sure to consider that. So it would be 180 plus 84 minus 45 all over 240. Yeah, and I think I saw better for saying that. Okay. Okay, so another thing that we need to keep in mind when calculating these is whether they are mutually exclusive or disjoint. So mutually exclusive events are events where the probability of both events occurring at the same time is 0. So that means that the and of the two would be 0. And sometimes that is represented with two circles that are not connected because they have no overlap. There is no intersection between them. So an example of this is someone cannot both like skateboards and dislike skateboards. So if someone could give me an example of what would be the other pair of disjoint events in this two-way table, or what would be another example of disjoint events from this two-way table? Okay. So the other example, I know some people saying in the chat as well, liking snowmobiles and not liking snowmobiles, those don't have any overlap either. So that would be another example of mutually exclusive events. Okay, next slide. Okay, independent events are events that do not influence each other's outcome. So what that means is that P of A and B is the same as P of A times P of B, or P of A given B is equal to P of A. So that means that one event occurring does not affect the other event occurring. And only when that is true, like only when they're independent, can we use the formula that says P of A and B is equal to P of A times P of B. So if they're not independent, we can't use that formula. And then if they are independent, P of A given B will equal P of A. So that means that if we want to know whether two events are independent or not, we can see whether P of A given B is equal to P of A, and vice versa, P of B given A is equal to P of B. Okay, so an example of this is if the probability of liking snowboards given disliking snowmobiles, it equals 45 out of 55, which does not equal P likes skateboards equals 125 over 160. So that means that the probability that you like skateboards is not independent from P dislikes snowmobiles. So a task for you guys is to use the P of A and B equals P of A times P of B to confirm if P likes skateboards and P dislikes snowmobiles are actually not independent. So use that formula to see whether they are independent or not. Okay. Yeah, so if you use P of A and B equals P of A times P of B, you would find that they're not equal. So that means that P liking skateboards and P disliking snowmobiles are actually not independent. So one thing about these formulas is that you can use them to determine whether they're independent, or you can use them if you already know they're independent, you can use them to find out different things about your data. Or about the probabilities. Okay. Next slide. Emily, do you want to get started on this one?
Yep. Okay. Can we get the first question up, please? I can start reading first. A little known fact is that Pep is a candy connoisseur. His favorite type of candy is gummy worms. Below, Pep has gathered data from a few gummy bear brands and is working to determine the color breakdown of each brand. Let's get the first question up. All right. Pep is drawing out one gummy bear from his bucket of all gummy bears. Find the probability of each of these events. Probability of red, probability of trolley, probability of red or, I believe that's a word, trolley, probability green and trolley, and probability of blue and trolley. Make sure you guys put these in split so we can check all of your answers. I see some good red answers that I will begin pinning. Righty. Good job, everybody. And then we're getting in with the trolley answers. Good job, Tara. All right, all of your answers are really good so far. If you're looking at this question like you don't know how to do it, at least give it a try. We won't judge you if you get a wrong answer, but it'll help you be more interactive with what we're teaching. All right, let's go through 1 and 2 first, since I think I see everybody has those. Alrighty, okay, so probability of red is 78 over 383. So we're not looking with any given or any total, or we're not looking for any given or any and or so far. So it's just red. So we're going to look at the total down here, which is 383, and we're looking for just the color red. So we're going to go over this red horizontal, and we are going to look at 78, which is the total amount that are red, and we're going to put that in as the numerator, and we're going to put 383 as the denominator. All right, 2, probability of trolley. We're just going to go down this column right here, and we have 150 out of 383 are trolley, and that is our answer for part 2. I believe we can go over part 3 as well. Thanks, Jed. Alrighty, so we're looking for red given trolley, or not, sorry, yes, red given trolley. So how many trolley in total do we have? It's 158. That's the total down there for trolley, and we're looking for red trolley. So there's 22. If we go down that the red horizontal, we're going to see 22 over 158. Okay, part 4, green and trolley. So we're going to look for the total that are trolley first, which is 158. Or sorry, we're going to look for the total overall, which is 383, and we're looking for the intersection of trolley and green, which is 102. So we're going to do 102 over 383. You guys can put these as decimals or fractions now. They might ask for the certain just a fraction or just a decimal on the AP exam, but for now, either one works. I think we can move on to 5 as well. I see some answers in the chat. All right. If we go down that trolley column and we're looking for that intersection with blue, there's 0. And the total is 383. 0 over 383, 0 over anything will be 0. So there are no blue and trolley. Good job, guys. I saw basically all right answers in the chat. Are events red and trolley independent? Use 2 of your answers in part B to justify your answer. All right, we have a question. All right, thank you for repeating that. All right, so why is probability of green and trolley not just 102? So I talked about some basic like restrictions of probability, and one of them is that probability is between 0 and 1. So it either 1 is like it happens every single time, like a coin that's tails on both sides. It happens every single time. It has to be tails. Or a coin where you're flipping for heads and it's tails on both sides. You're not gonna get any heads at all. So it has to be between 0 and 1. So why is probability of blue? Can someone repeat that question? I'm sorry. Thank you. Probability of blue and trolley is 0 because we're having 0 over 383, and any 0 over anything is gonna be 0. That's a math term, not a stats term. But green and trolley, we're basically looking at the intersection of green and trolley. So that's 102, and we're looking at probability of green and trolley over like all of the rest of the gummies. So it's gonna be 102 over 383. Blue and trolley is 0 over 383, and that simplifies to 0. All right, back to our independent question. I'm seeing a couple answers in here. I'd like to see a couple more. All right. Let's put up some answers. This one is good. This one is good. Alrighty, you guys are really mentioning how let's pin this one again. Probability of red and probability of red given trolley are not equal. So that is our determinant of if they are dependent or independent. Make sure you use the values for probability of red and probability of red given trolley when you're explaining it on the FRQs, because you could just guess and say, oh, they're not the same, but you need to prove with the quantitative data that it is true. If the probabilities, yes, Ethan, if the probabilities are equal, then they are independent. Yes, Jed. All right, next. Are events blue and trolley mutually exclusive? Use some of your answers in part B to justify your answer. I believe that's supposed to be in part A. All right. Everybody says yes, it is mutually exclusive. Why? Because the probability of blue and trolley is 0. So we found that in part A4. No, 5. My Roman numerals are not on top of things. But at A5, we find out that the probability of blue and trolley, the intersection of the two is 0, which means they cannot happen at the same time. Good job, everybody. And remember, that's disjoint. It's break time. All right. Alrighty, we are back. All right, we're going to be talking about continuous random variables now. So a continuous random variable can be any value within a certain range. Probabilities usually apply to a range rather than a specific value. So the example they want to use here is that for height and time, you can't have an exact integer. Like, you can't be like either 50 or 51. You could be like 50.5 or like 50.25 or something in the middle. Like, it's not just integers, there's points in between as well. So it's very continuous, which is why it's called continuous random variable. Sorry, I was reading off Ethan's comment there. Next. Distributions. All right. Interpreting probability distribution of discrete random variables. I talked a little bit about shape earlier in preview night 1, but let's go over a little review. Roughly symmetric is something that is bell-shaped. So bell-shaped is like this, and its normal distribution is the same on both sides. So it's not like the mode's on one side and then there's nothing on the other side. The mode is in the middle, and then it's shaped like a bell curve. Double peaked, we have two distinct groups of values within the variable. So that could be like two modes, like bimodal, and then single peaked, one dominant group of values could be like a unimodal graph. Right skewed. So we want to call this the positive skew. The skew is the tail on the right, so it's skewed towards, there's the skew towards the right end, and the most of the values are on the left. Our left skew, on the other hand, is where all the values are concentrated on the right. The tail is on the left, hence it is skewed towards the higher values. Don't forget, when you're mentioning the when you're mentoring socks, you want to talk about the mean and the variability. So make sure you use mean to describe, and then variability also to describe the spread. All right, let's talk about discrete random variables. So this can only be a specific discrete value. So like the number, so like it can't just be like 0.5. Like you can't have half a student in class. These formulas look really terrifying. I'm going to try and break them down for you guys. So first we have our mean or expected value of variable x. So if we look at this graph over here, we're looking at x times probability of when the big X equals little x. So the expected value for this would be 0 times 0.18 plus 1 times 0.34, blah, blah, blah. You add them all up, and the value you're going to get is the expected number of goals you get, if you guys understand what that is. Alrighty, our variance, this one is a harder formula, so we have x minus e of x squared times probability of when big X equals little x. And then our standard deviation is the square root of variance of x. Remember, the standard deviation is the square root of variance of x, and the variance is standard deviation squared. Let me grab Miriam real quick. Alrighty. Next. Distributions. So one of our distributions is a binomial, and our assumptions for a binomial distribution is that there are two possible outcomes, so success or failure. So there's only two. The trials are independent, so you can't be like, oh, because of what happened in the previous trial, the probability for this one might change. Our probability of success is the same for each trial, so this builds off kind of the independent part. So like flipping a coin would work on this one. And then models the number of successes in a fixed number of trials. You have to declare how many trials you are doing. Our mean is mu of x equals n times p. Standard deviation is sigma of x equals root np times 1 minus p. Remember, these two are on the formula sheet, so if you can't get them in your brain, that's okay. You can always go back to the formula sheet, and this will help you a lot. And then our formula over here on the right, this you guys can look at if you want to understand how it works, but you guys can always do it on your calculator. Your calculator is your best friend for AP Stats. Next slide. Alrighty. Using a normal distribution to approximate a binomial distribution. So we want n times 1, np times 1 minus p to be greater than 10. So there's either np and p times 1 minus np. Both have to be greater than 10. Both of them need to be greater than 10 for our for it to be a normal distribution. If that doesn't work, we cannot. Let's do a practice question here. Let's find the probability of at least 150 favor a charter school. All right, can I get some answers for you guys? Sydney gave a formula. Let's see if that formula is correct. Just a tip for the FRQs, I remember my teacher said to show that you're using a calculator for binomial CDF, you want to write what, let me highlight, what they did. So binom CDF, 300, 0.53, and 150. Make sure you say that. Don't just be like, oh, the answer is this. And Mr. Argo says label the calculator, speak all of it. All right, I've gotten a couple 0.1627, which I am going, maybe I should check you guys. Let's check you guys real quick. Ethan, if you want to be safe, you can do that. It might be a minute, but sorry guys, I gotta check this. All right, 300, 0.53, and 150. All right, I got 0.1627. Alrighty, we can go next slide. That looks good to me.
Okay, so instead of binomial distributions, now we're going to be looking at geometric distributions. So the assumptions, a few of them are the same. So 2 possible outcomes for each trial, success or failure. Trials are independent, and the probability of success is the same for each trial. And it models the trials needed until the first success. So how many trials do you need to get until you get one success? So the mean for it, which is represented by mu of x, which is the random variable, is equal to 1 over p, which is the probability of success. And the standard deviation for it is sigma of x, which is equal to root 1 minus p over p. And these both are on the College Board formula sheet, so you do not have to memorize it. Okay, so combining variables. If you're given a random variable x with mean e of x and standard deviation sv of x, transforming it into a random variable y by adding a constant c. So if you're adding or subtracting C, the mean will be increased by C, but the standard deviation will just stay the same. And if you're multiplying or dividing it by C, the mean will be multiplied and the standard deviation will also be multiplied in this case. And then given random variables x and y, where you have two random variables with mean e of x and standard deviation sd of x, when you're combining them, the mean or the expected value will be equal to the result of adding them together. And the standard deviation will be equal to the root of each standard deviation squared, and then you add them together. An important thing to notice is that when the standard deviation, even if you're subtracting a random variable from another random variable, the formula will still be the same. It will still have an addition symbol in between the two squared standard deviations. And the overall shape does not change when you're adding or subtracting or multiplying or dividing a constant to a random variable. Okay, so yay, now we get to do some Unit 4 review. So how do you calculate probabilities from a two-way table? You guys can type your answers in the chat. So if you have a two-way table, how would you calculate it? Okay, yeah. So some keywords that you need to be looking out for, like Mr. Argo asked, is and, or, given, neither, or both, which are some key things that you should look for in questions asking you about probabilities for a two-way table. Okay. How do you prove independence or mutually exclusive from probabilities? So there were two formulas that we learned about. So if you guys could type those in the chat, that would be great. Okay, so some people are saying that P, A, and B equals the probability of A times the probability of B. And there's another one. Oh, okay, I see it now. Okay, somebody says for independence, P of A, no, P of A given B is equal to P of A, and then also P of B given A would be equal to P of B. Okay, how do you find probabilities given a binomial or geometric setting? You guys can write out which calculator function you might use, or just write out the formula if you want to, I guess. Yeah. Okay. A lot of people are saying binom CDF and geomet CDF. And if you use, I think we might be talking about this a little later as well, since Mr. Argo is going to do like a calculator tutorial. But for if you're using a TI-84, the binom PDF finds a probability that exactly X successes occurs within the number of trials. And then if you use CDF, it finds a probability that X or fewer successes occurs during a certain number of trials. So if it's asking you for exactly blank number of trials, you would probably use binom or geomet PDF. And if it was asking you whether it would be a certain number or fewer trials, it would be CDF. Okay. So we also learned how to use rules on combining random variables to find new means and standard deviations. You guys can just say like one rule you guys remember about either adding a constant to a random variable or adding, subtracting, multiplying two different random variables and how that changes the standard deviations or the means. Okay, I see some good answers in the chat. So the standard deviations do not add, but if you have a mean and then you add a constant, you would add the constant to the mean and get the new mean. The shape is always the same. And for standard deviations, when you're adding two random variables, you would square them and then square root. Yeah. Okay. So we also okay, yeah. So we're gonna go through another one of Pep's statistical escapades. This is everyone's favorite, I know, doing FRQs. So for this one, Pep just recently got a job at a car factory. He is in charge of the new jalapeno. In his time at that factory, he has discovered that the axles come off of the factory at a rate that is normally distributed with a weight of 160 kilograms and a standard deviation of 20 kilograms. Okay. What is the probability that Pep randomly selects an axle that weighs more than 175 kilograms? So for this one, pay attention to the fact that it's normally distributed, and then they also give you some more information. So you can use that to help you figure out the answer. Okay, so since it's a normal distribution, the mean is 160 and the standard deviation is 20. So the probability that x is greater than 175 would be equal to 0.2266. And the way you do that using a calculator is that you would use normal CDF function and then just put in the lower as 175, the upper as just a really big number. Over here we just put like a bunch of nines. And then the mean is 160 and the standard deviation is 20. So then you would get the answer, which is like the area under the normal curve. So for the next part of the question, Pep decides that he's going to randomly select 10 axles. What type of probability distribution would we use to determine the number of axles out of 10 that weigh more than 175 kilograms? Okay. So for this one, we would use a binomial distribution since we have two clear outcomes, either more than 175 or not more than 175. So that's our like success and failure. And the axles are independently selected from each other. So each axle has the same probability of being chosen, which is 0.2266, like we just calculated. And there's a fixed number of trials, 10. So these are all the conditions that we would need to use, that we would need to state in order to use a binomial model to represent our distribution. Okay. Now find the expected value of axles out of 10 that weigh more than 175 kilograms. Okay, so here the expected value is 2.266 because the way we calculate it is by multiplying 10, since that's the number of trials, times the probability of success, which is 0.2266. So that's the formula we were looking at before for the mean or the expected value of a binomial distribution. And it is on the formula sheet, so you guys don't have to worry about memorizing it. Yeah. Okay, next question. What is the probability that at least 8 of the 10 axles weigh more than 175 kilograms? Okay, so for this one, we're still using a binomial distribution with n equals to 10 since there are 10 trials, and p equals to 0.2266 since that is the probability of success. So the probability of x being greater than or equal to 18, we find that by doing 1 minus binom CDF. Because since we're asking for what the probability of at least 8 of the 10 axles are, we would do the complement of the probability of at most 7. So when you do binom CDF, that gives us the probability of having 7 successes or less. So then the complement of that would be 8 successes or more. So that's why we do 1 minus binom CDF. And then we need to write in our parameters, which are n equals 10, p equals 0.2266, and x equals 7. And after we subtract that, we get our probability, which is 0.000197. And the reason it's 7 for x is because we want to find a complement of at most 7. Okay, so part E is asking, is your answer in D a surprising result? Like, is it surprising that the probability is low. Okay, I know a lot of you guys were saying in the chat, so yes, this is a surprising result because the probability is less than 0.05. Sorry, the significant result.
All right, we have 55 people in here. We have 32 in here. Let's get a little more participation. Let's get to 40 and then we'll start. And just a heads up, we're not going to be doing all the questions. We'll be doing about 6 to 7 and then, or 5 to 6, and then we'll be doing some calculator review because you guys are complaining about that and I feel like it'll be useful. All right, I think we can start. Let me try to talk over this music. In a simulation to estimate the probability of drawing at least one ace and 5 cards from a standard deck, which method best represents the use of theoretical probability to compare against simulation results? we can reveal pretty good probability, or not probability, percentage of accuracy. So we have a little split on C and D and a little bit on A. So which method best represents the use of theoretical to compare against simulation results? So this is the at least one question. So when you see at least one, you want to do 1 minus the probability of drawing none. So this is a complement type of question. Make sure you guys remember, if it's at least 1, you're going to subtract 1 minus the probability that none occur. Sorry for not mentioning this one earlier. Alrighty, y'all did really good on this question. These are very wordy answers. The answers in the AP exam will be a little more straightforward, but this is still really, really good practice. Good job, John. All right, so we have a little split on A, C, and D, drawing n slips without replacement, noting pairs that match, having n people state their birthdays orally and determining if there's a match, choosing n days randomly, then observing. All right, so our correct answer is randomly assigning birthday numbers between 1 and 360 to n spots and checking repetition per trial run multiple times. All right, a school club has an equal number of juniors and seniors. If 2 members are randomly selected for a committee, what's the probability that they are from different grades? Okay, we're gonna skip this one. As Jed says, the choices aren't latex compatible, so it's a little sketchy. That will not be on the AP exam. Okay, back to the easy stuff. If events A and B are mutually exclusive, what is the probability that both events happen simultaneously? All right, begin reveal. All right, we got a couple wrong answers, but that's like 3 people. That's okay, you guys. If you guys get the answer wrong first, you'll get it right on the AP exam. So it's okay. Make your mistakes during practice, not the actual test. All right, so if they're mutually exclusive, it literally means they cannot happen at the same time. So the probability they happen at the same time is 0. Next question. We're going to do question 5 and then question 6. So question 5, if a student is randomly selected from an AP statistics class, what is the probability that the student received an A on the final exam given that they completed all their homework assignments? What's that given? All right, we can reveal this one. Good job, everybody. Okay, so we know that given is this vertical line right here. So C and D, they're just gone. They cannot work at all. All right, so we either have A or B. Both of them are given. But what's given? Given that they completed all their homework assignments, which means that is going to be on the denominator. There's only one right answer, and that would be A. So the given is always in the denominator. Good job, though, guys. That's pretty high accuracy. All right, we have 30 of 33. Let's wait 1 more minute. Come on, if you haven't answered, go for an answer you think might be right. All right. I guess our 3 will not be in there. Oh, we got 1. All right, we can reveal. We can just reveal. All right, 77%. Good job. All right, so we have Mostly on D, and then B says if probability of spam given keywords is bigger than probability of spam, this implies that those keywords increase our belief that this message is spam. All right, so we know the equation is the bottom will be keywords. The bottom will be keywords, so if we have that being greater than probability of spam, that will increase keywords. And Mr. Argo says, if the probability of it being spam is higher when there are certain keywords, we can filter out spam better based on those words. Alrighty, we are going to move on to some calculator work. If we can get Mr. Argo on stage.
All right, everybody. Fantastic work tonight. Whoa, that was awesome. That was awesome. So one of the biggest feedbacks that we've gotten in our CRAM sessions was to go over calculator work. So I have tracked down a computer that has the calculator software on it. So we are going to go over some key functions with the TI-84, and then we will transition to the TI Inspire. So just so you know, if I were to be a calculator, I would not be a TI. I am a NumWorks guy. If you don't know about NumWorks, it is the online applet is free. It's really great for AP Stats, and the real calculator you can use on the exam. So I have transitioned from TI to the NumWorks, but TI is great, and I know that's the standard product that we're mostly would use. So TI, here we are. So we're on the TI-84, and you can see I did a question earlier. Let me clear that out. So the key buttons that you're going to want to be familiar with in the TI calculator. The first thing you would need to know how to do is to put in a set of data. So in order to do that, if you press the stat button, you can see it highlighted over there in red. And the first thing that pops up under the stat menu is the edit function. So I'm going to hit enter, and then I have some data from who knows when typed in over there. And that's how we would type in data. So let's say we have a data set of 8, 5, 2, 1, 4, whatever. That's our data set. Okay, so if it's a one variable data set, that would be how you would type that in. So again, that's stat, and then it's the first option, edit. We really don't need the sorting options for AP Stats, so we don't have to worry about that. And once you have typed in your data, that's where some of the calculating comes into play. If you want to be able to calculate the mean, median, Q1, Q3, all those one variable stats, you will go press the stat button, scroll over to calculate, and that first option, one variable stats. I do not have a frequency list in there. All I have is my L1 as my data. So I'm going to do list L1 and then enter, and it gives me all the things that I need from that fake data set that I just typed in. So I can see my mean, that's your X bar, is 3.857. We don't really use the sum of X or the sum of X squared. Our standard deviation, as if it were a sample, is 2.41. If we treat that as a population, it's 2.23. Our sample size is 7. Our minimum's 1, Q3, 2, 4, 5, and 8. Okay, there's your 5-number summary there at the end. So that is how you can calculate data. Remember last night when we did the PEP statistical escapade question with the inches of rain, and we had to find the 5-number summary? This is exactly how you would do that in your calculator. And I tell my students, spend the time. That's an easy question. Determine the 5-number summary. If they happen to throw you that softball, take the time to type it in your calculator and make sure you label your answers and get everything perfectly correct. And it's going to take a little minute, but it's going to make sure you get the E on that portion to get the full credit. Now that I have that data set kind of calculated, let's say I wanted to create a box plot. So if I press second, and up here in blue, you see we're above the y equals that you would typically use to graph algebra equations, things like that. You have the stat plot function. And I want to make sure that stat plot 1 is on. And I can do a scatter plot, which we only have one variable here, so that doesn't make sense. We never use little connected line graph. Histograms are okay. Box plot is the more common one. And in AP Stats, we want to use the box plot that has the dot, because that dot is going to tell us our outliers. Okay, the non-modified box plot we don't really use. And then the last one is a normal probability plot, which very, very rarely shows up in AP Stats. So we, again, for time's sake, we don't really go into that. So once you've done that, and we have plot 1 turned on with L1 as a box plot, if I go to, if I hit graph, okay, I can see some of the box plot. The easier way of doing it is to do zoom and option 9, zoom stat. So zoom 9, it gives you a great picture of the box plot. Okay. So that is the best way of how to create a box plot, create your 5-number summary. If you hit trace, you can trace out the different parts of the box plot, which is fantastic. If you want to make sure you're labeling your box plot correctly, last year's free response question, you had to draw out a box plot. So you could have used this as a tool to make sure you bank as many points as possible on that. So yeah, good stuff. All right, so that is basically how you do one variable data in the TI-84. And I know there's a lot more stuff, so we're not done. Let's see. I kind of lost track of the chat there. Student hosts, if you see a question that's really good and you want to pop it up on the screen, feel free to do that. I appreciate y'all moderating the chat while we're doing this. So the other type of stats that you might have to do. So actually, let's do this real quick. So I'm going to put in an outlier that is just like obviously an outlier. Let's say 22. And then if I go, now you can see the box plot and the dot over there is clearly an outlier. So it does that Q1 or that 1.5 IQR formula for us and shows that it is an outlier for us. So it kind of does a little bit of that for us. And if you trace it, oops, let me hit trace first. Median Q3 X equals 8, which is the highest data point that's not an outlier, and then our maximum, which is an outlier. So you see that separation there. Okay, so that is a 1 variable data set. Another data set that you might have would be like a 2 variable data set that you would want to do, say, a scatter plot for, calculate the slope regression, which honestly does not happen on AP Stats very often. But while we're in this kind of realm, we will touch on it. So when we get an outlier on the calculator, what should we write on the free response? So when you're drawing out your box plot, you would draw it out the same way there. Now, if you see an outlier on a box plot and it asks you on the AP exam to determine if there are any outliers, drawing the box plot and saying there's a separated dot is not proof enough to show that there's an outlier. You need to write out the formula like we talked about last night in the escapade for that particular aspect of the problem. So you can't just draw the box plot and say, oh, there was a dot, so it's an outlier. You have to show the formula. I know that kind of stinks, but that's it is part of it. Every now and then there's been rubrics where they're like a little bit more lenient on that, but I would not bank on it at all. I would do the formula that John just put down there in the chat and do that. If anything is less than that or greater than that, it's an outlier, which obviously 22 would have been here. Okay, so if you needed to create a scatter plot, so you got, this is going to make a really funky scatter plot, but that's okay. Oh, I put one too many points. I'm still Samosoing in my head. I have been since last night. Go away. What are you doing? Delete. There we go. All right. So so now I have 2 lists, L1 and L2. And I'm going to go to stat calculate, and I want to go to, we only do linear regression in AP Stats. We don't do quadratic, cubic, quartic, natural log, anything like that. So either option 4 or option 8. AP Stats is going to show up more like option 8, where it puts the y-intercept first. And so the X list is L1. That's what I put in as my X list. My Y list is L2. And then I'm going to go down to calculate. And then it gives me my y-intercept, 3.978, my slope, negative 0.0576, my r-squared, which is terrible because I made up data points that weren't linear, and my r, which is also terrible for the same reasons. Okay. If you are having issues with your TI-84 and you're like, hey, I'm not getting r and r-squared, there's a weird little setting that's turned off. To make sure you get r and r-squared, you're going to go to mode and make sure that stat diagnostics is on. Okay. I know I'm going through all this very quickly. The replay will be available afterwards. So if you need to, oh crap, I don't remember what that was, you can go back and watch the replay in this last little 30-minute session. Okay. So that is basically everything in the stat section, that stat button that we would use. At least for the first half of the class that we've covered in the past 2 nights. We might do another one of these after maybe night 4 or during night 5 on the test function, which is your confidence intervals and hypothesis test, but we'll hold off on that for now since we haven't covered it in class. When you select the graph model, there's 2 that look like a whisker plot. It is the whisker plot that has the separated point, and I'll pull that back up. So it is the 4th one. So see the 4th one, how it has that separated point and the 5th one does not. We want to pick the one that has a separated point. That will show us that outlier for us. Okay, so that is in about 10 minutes how you would use the stat button on the TI-84. Okay, the other main button that you're going to use besides just, the numbers that we all know how to use is the distribution function. And the distribution function right here is going to be one of the key parts that you would use. So to access that, you're going to press second and then the vars, which pulls up the distribution menu. And the first thing you see is normal PDF. We don't use that. No normal PDF. So skip that one. Don't ever use it. We have normal CDF, which most calculators will pop up and give you the menu. The computer applet doesn't do that. So the first thing you would type in, it would ask you for your mean, your standard deviation, your lower and upper bound. So let's say 0 to 100. That's my, or we'll do 0 to 10. 0 to 10 is my lower and my upper bound. And then let's say a mean of 5 and a standard deviation of 2. Okay. And then it will calculate my, probability for us. Again, most calculators, it's going to pop up with a menu that asks you what the lower bound is, what the upper bound is, what the mean and the standard deviation is. And so yeah, that is your how you would do normal CDF. We do not do normal PDF. Okay. If you want to find if you want to go backwards and you want to do inverse norm, see, this is the kind of menu that I was expecting to see with normal CDF. So always area to the left, so 0.25, mean 0, standard deviation 1, so standard normal curve. Some options, some software options will ask you area to the left, in the middle, or right. By default, it is the left-hand area. So press enter, and then it tells you that 67 or well, 25% of the data in the standard normal curve is less than negative 0.67. So essentially it's the z-score there. Okay. So that is that. And so let's see. So in the distribution menu, also over here, so inverse norm and normal CDF, inverse T and T CDF, we could talk about those after we do inference. Actually, we'll talk about that on Sunday night when we get to T-scores. Chi-squared, same thing. We do not do F-scores. So binomial PDF and CDF. Okay. So binomial PDF, and we talked about this in the chat, that is when you are finding the probability of a binomial. Let's say we had 20 trials and we are looking for, let's say maybe a 40% success rate, and we're looking for exactly 10 successes. So 10 out of 20 times we were successful if we had a 40% chance of being successful. And then you can hit paste and it calculates that one individual probability for you. So that's binomial PDF. If you use that notation, label, 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 you have to label your calculator speak. You will lose points, and in fact, maybe not get any points if you just wrote what you saw on your calculator. It's a great tool, but you have to label your stuff. That's the biggest thing with this little 30-minute calculator thing I can give you, is label what you're using. All right. Anyways, yes, label, label, label. I think there was a SpongeBob episode. Ladle, ladle, ladle. I always say label, label, label. Anyways, okay. That was stupid. All right. So in that same, oops, I hit the wrong thing. So in that same distribution menu, we have binomial CDF, inverse binomial. We don't use Poisson. Geometric is very all the way at the bottom. So CDF for both geometric and binomial are going to work they're going to take the inclusive, whatever you put in for X, it's going to find that probability and then go all the way to the left. So let's say we have 20 trials again, the probability is 40%, and our X value is 10. It's going to take the probability of having 0 successes, 1 success, 2 success, 3 success, all the way up to 10 successes and add up all those probabilities. This is like what we saw on the statistical escapades later. So then we would have that. On the TI-84, you have to, if you're doing greater than value, you're going to have to do the complement, which is what we did on the escapade. Okay, so that is TI-84 calculator in a nutshell when you are doing the first half of the course. If we need to, we can come back and go into this, the test menu, and talk about that for TI-84 after we talked about those on tomorrow night and Sunday night. Okay, so the TI-80 or the TI-Inspire, I'm sorry. So that is the 84. And again, we can touch on those things again a little bit later. All right, let's see. Let me swap my window that I'm sharing. I apologize, y'all. So TI-Inspire. So this is what the TI-Inspire looks like. I used the TI-Inspire for a few years. I used the TI-Inspire 84 for a lot of years, and now I'm on the NumWorks train. So whenever you turn on your calculator, you got these options here. If you want to put in data, you're going to want to go to Documents and create a new one, okay? We're going to be operating in the List and Spreadsheet options. And I'm going to name this, I know we did one on inches of rain. Oh, it's not going to let me do spaces. So we'll just say inches of rain with no spaces. Okay, and PEP observe 0, 1, 2, 3, 4, 5, whatever. Okay, so that's how you would enter in your data, similar to how we did the L1 and L2 before. If you need to put in an L2, you would go over to column B, name it whatever you want, and type those in. Okay. So now that you have your data typed in and you want to calculate those one variable stats for that, you would create another page. And a quick way to do that is to press Control. And then over here in the blue, you see that plus page option. So Control, add a page. And we want to, if we want to just calculate stuff, we can add calculator page. And this is where we would do all of our just regular calculations. So I'm going to go Menu, go down to Statistics, Stat Calculations, and and this looks the same as the TI-84. So one variable stats, I only have one set of data, and then my X list is inches of rain, and then it calculates all the lovely stuff for us. Okay, a lot of the stuff we don't use, but it does give you mean, which is your X bar, your 5-number summary, and your standard deviation. Okay, so that is how you would do that part in the TI-Inspire. So again, and if you want navigate pages, so like let's say go back and change our set of data, if you press Control and then the left on the little D-pad, it takes you back to that page within that document. So I told my students last year when they used the TI Inspire, as soon as you start your test, open up a document, create a spreadsheet page that you can put your numbers in, a calculator page to do your calculations, and then a third page, which we don't use a ton, but we could use it some, the data and statistics page, which you can create a dot plot really easily. Look how pretty that is. And it looks perfectly. Somebody want to put in the chat what shape this graph would be? What kind of shape we got? One word. Ooh, I had to scroll a lot. It is uniform. Thank you, Ethan. Woo! Yes. All right. Awesome. Yeah, it is uniform. Okay. Anyways, but yeah, so you have that and you can put those things in. So let's say on your data, you go back and you want to add in Y variable, candy eaten, clearly again, trying to put a space in there. Candy eaten, and let's say Pepe 12, 13, 14, 15, 16, 18 pieces of candy. I don't want to do 17 because that would be perfect. And I go to my my data and statistics page. I can make my Y variable candy eaten, and then you can see my pretty good linear setup, which we have there. Okay, and if we go back to our page and we want to do the scatter plot math, the R and the R squared and things like that. So we're going to go to statistics, oh, I clicked the wrong thing. Stat calculations, linear regression, either one of them are fine. Inches of rain, candy eaten, hit OK. And it gives you all of your data. You don't have to do the little stat wizard thing on the Inspire. That's one of the benefits to the Inspire. Also, another benefit, if residual plot, once you have done the linear regression model and you go back to your scatter plot, it will allow you to change the y-axis to the residuals. Okay, and you get your residuals, which this is not a great residual plot because the data set was just kind of quick and made up. It does show a pattern, even though it was a linear model, just due to that way that worked. So that's how you put data in, create different graphs. If you wanted to change the type of graph and you want to press menu and plot type, if you only have one variable, you can choose dot plot, box plot, histogram, normal probability plot, and all that good stuff. Okay, so that is the one variable stats portion. If you are on the Inspire and you are doing the calculator for probability, another thing I liked about the Inspire is you have to do is that it's a little bit easier. So you're going to go menu. You can go to stats. You can basically go menu stats for anything on the calculator page, which I really like. In the TI-84, you have to go menu distribution or stat over to calculate. In the TI Inspire, it is menu, statistics, everything's there. It's also in the probability section, but you have to ever go to that. You can go to stats every time. And you can go down to distributions, never normal PDF, no normal PDF, normal CDF, you got your little menu there, okay? Type in your stuff, label for your response. And if you are doing, let's see, inverse norm is the same way. That's how you get to the menu, and you would type that in. Okay, and let's see, we have binomial, PDF, and CDF. With binomial and geometric CDF on the Inspire, this is one of the things I really liked about it. It allows you to put in the lower and upper bound. You don't have to worry about that weird complement rule like you do with the 84. Okay, so the number of trials that you would have, you know, we said 20, probability of success is 40%, and we want to find the probability that's more than 9 of, or at least 9 of the 20 trials were a success. We can go 9, and our upper bound's 20, and There you go. It gives you the answer for the binomial probability. As long as you label n equals 20, p equals 0.4, lower equal 9, upper equals 20, you're good to go. Stats readers know that if different calculators, different ways of labeling, they are going to grade on if you had the word binomial, which is hopefully you have that in there, okay, regardless. They're going to check to see that you have the parameters, the n and the p, and they have to be labeled. And they're going to see if you have the correct direction for the probability and then the answer. Those are the 4 things they're going to look for. For the direction, if you have lower 9, upper 20, good. If you have 1 minus binomial blah, 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 x equals 8, you're good. If you have p parentheses x greater than equal to 9 parentheses equal, then you're good. A two-way chi-squared test on the Inspire. That's kind of a weird one. That's one of the only ones that's not very family friendly, or not family friendly, not user friendly. That's the word I'm looking for, not family friendly. The only one that's not very user friendly on the Inspire. So the way you would do that, okay, so we're in the calculator page. We are going to go to our little matrix menu right here. Okay, and apparently that was the last thing I did on this app because the matrix is the first thing that popped up. And I'm going to put in my, how many rows and columns. We'll go 3 by 3 is fine. And I'll type in my numbers. 88. I'm just throwing stuff out here, y'all. 12, 7, 6. All right, so once you've entered in, this would be your observed counts. Once you enter in your observed counts, you want to store that matrix as something. So I'm going to go to the store option, which is in blue. So I'm going to press Control and then the var button, which is store. And I am going to store this as PEP. So my observed matrix in my calculator is now named PEP. And then to actually run the test, you are going to go Menu, Stats. We're always Menu, Stats, and TI Inspire, which is nice. Scroll down to Stat Tests. Go to chi-squared two-way tests. It asks you what your observed matrix is. We are going to select PEP, and there you go. All right, you have your chi-squared test statistic, which is obviously very high and resulted value. If you want to pull up the expected matrix, because you need that for that condition of inference, because they all have to be at least 5, you can go to, yes, you can press var and go down to expected matrix. And it tells you this is what they should have been. So I shouldn't have been able to run this test because my expected values were not all of these 5. That's probably why we got a significant outcome. But that's how you operate the test. And just remember, if it's independence, name it chi-squared test for independence, or association, same thing, or test for homogeneity. And we'll talk about that on Sunday night. Okay, that was a calculator crash course in, we're 2 minutes past 9 o'clock, but what, 32 minutes? I don't think I've ever done so much calculator stuff at one time. All right, student host, were there any other questions that I missed?
I think we are good. There's some lingering questions in the Q&A, but I think I got most of them down.
Good deal. That's good. All right. So make sure before you head out that you take that survey down in the call to action, that green survey button, so we can know how we can improve as the week goes on. Great work tonight, everybody. Fantastic. Can't wait to see everybody again tomorrow night as we continue and get into inference, which is the fun stuff in AP Stats for me. Great job working through probability tonight. Y'all have a good night.